Hello and good afternoon. My name is Nandan Joshi and I will be presenting the results of my course project. The objective of my course project was to develop a CFD solver in GPUs. I did that using CUDA. The idea was to develop a solver that is fully parallelizable with as many threads are available in CUDA. So before I go into the results of the presentation, I would like to give a little background of the project, especially to those who do not know what CFD is. So this is a little background of CFD. So first of all, what is CFD? CFD is basically a method of solving fluid flow equations. And why do we need it? Is because in general, fluid flow equations are defined by a set of partial differential equations which are non-linear in nature. So here I have put the Navier-Stokes equations uh, which describes the fluid flow for a two-dimensional domain. So as you can see there is this particular term here, u gradient of u, which is basically a non-linear term, and thus there is no method available to solve it analytically. So that is the reason why to solve this equation we need to make some computational approximations, and the way it is done is using linearization and using discretization. So basically we know that the differential equations itself cannot be solved. So what is done is, in the geometrical domain, we define discrete points at x and y locations. This is called a grid, which is drawn here. So for example, at we index it as I comma j. So at this particular point is I comma j. The point next to it in the x direction is called I plus 1 comma j. The point above it j plus 1. So we discretize the domain into geometric discrete points, and then we use these points to linearize the partial differential equation. And once we linearize it, it is basically just a set of linear equations. And to solve it a, requires a matrix solve. So this, of course, this is not solved directly because that is an order of n cubed algorithm. There are iterative algorithms available to solve linear equations, which give the result much quicker. One example is the biconjugate gradient method, which I have applied for this project. So the main idea of these iterative linear solves is that it uses a combination of only matrix vector multiplications. And as we know that matrix vector multiplications are fully parallelizable because they employ the single instruction multiple data paradigm. So using SIMD paradigm, we can fully parallelize matrix vector multiplications. That is what the approach that has been used in this project. That the GPU threads, the problem is split into different GPU threads, and using this SIMD paradigm on the linear solve, this code has been parallelized. So next I'll move to some details of the equations used and the details of the algorithm. So I'll go over an overview of the algorithm. I have already gone over the overview in detail in the report, and I don't want to spend the entire presentation on going into the details of the derivation. So this is just a brief overview of the steps taken in the algorithm, and in the next slide I'll go over the actual pseudocode. But basically the key pattern to note here is that the equation, the Navier-Stokes equation that I highlighted before, that can be broken up into 4 parts. So the first part, the u gradient of u, that is an advection term. It basically denotes how the fluid velocity is carried with due to the velocity. So the force of the velocity itself. The second term, the on the right hand side, the mu rho gradient square of u. This is the diffusion term. This kind of denotes how thick a fluid is. If it is more viscous, its diffusion is more, which you can see by this mu factor, which is basically the viscosity of the fluid. Then there is the pressure term, which denotes the how any external pressure, like say a pump, if how that influences the motion of the fluid. And finally, there is this temporal term, which basically takes into account that the fluid would change its properties with respect to time. So solving this equation and linearizing these equations is basically done by taking advantage of these 4 parts. Now if you note closely, you can see that this term, the advection term, is in particular non-linear. So we want to avoid the non-linearities, and that is handled by what is called as an Adams-Bashforth method with a two-step discretization. So I have gone into the details of its derivation in my report, but the key idea is that it is split, is that this time discretization is split into two. So basically what we do is, instead of solving this entire equation in one step, we split it into two steps. The first step is where we solve for an intermediate variable velocity which is called u star. Un denotes the velocity at time equals to n. So at the current time step, the value of which is known. All the values with a superscript of n are known, and those with a superscript of star and n plus 1 are to be solved for. So here, basically, we in the first step we split this. We do not consider the pressure term in the first step. We split it into just the diffusive term and the convective terms. So it is expressed as a convective term with superscript of n minus 1. So which means we have both these values are known. We don't need to solve for anything. H is basically a simplification of the advection term, and the actual value of h is denoted here, which is basically the integral of the u square, or basically u dot u, since u is a vector, or the integral of that over the face of one particular cell. That is what h is. D is basically the diffusion, so the value of D is given here. It's the gradient of the velocity at each of the face. Now if you can see, n minus 1 are known, so we don't, so this is like a constant term at each time step. Dn is known, that is also a constant term. This d star is a value that we need to calculate because it is unknown. So u star, d star, so thus u can be this basically forms one linear equation which needs to be solved, and in this equation u at any particular grid point I comma j is dependent on its neighboring points. So this is the first equation that needs to be solved. And in the second equation, the second step, un plus 1, which is the time at the next time step, is solved by this is solved, or basically I would say is updated with this S value, which is the pressure value given here, which is the gradient of pressure basically. Now please note that I just wanted to simplify these equations for understanding, so I haven't included any of these constants in the derivation, but basically the d term is multiplied by mu by rho, and h term is divided by rho. That's something that we need to know. So now I said that we have to solve for this gradient of p. The question is, how do we do that? Because here it's only one equation and there are two unknowns, u and p. So p is an unknown. So to do that, we have to use the continuity equation. So for an incompressible fluid, the continuity equation states that this gradient of u is just 0. So if I plug this thing into this equation and I take a gradient, so we know that un plus 1, gradient of un plus 1 is going to be 0. U star, gradient of u star is not going to be 0 because in calculating that we did not consider the pressure. We calculated it in the first step where no pressure is involved. So but it is known because it has been calculated. So basically this equation reduces to gradient of u star is delta t into gradient of s, which is this term. So that's why it's called a two-step process. The first step is just we update the velocity based on the convection and the diffusion without considering the pressure. And in the second step, which is called a continuity correction step, the u is updated with this pressure value to satisfy the second equation, the continuity equation. That's the overview of the algorithm. Now next I'll just quickly go over the pseudocode. So this pseudocode is pretty much an extension of the process I highlighted in the previous slide. It's basically just a logical extension of the derivation, and it's implemented and the way it's implemented. So we start by just gathering all the inputs from the user, from a file, or from the command line, and then based on that we just create a dictionary that basically maps the type of cell, and that basically creates the type of cell. So if it is an interior cell, it's marked as an interior. If it is a boundary cell, we give an information of what the type of boundary, whether it is an inlet boundary, whether it is a pressure boundary, a wall boundary. I have given more details of this in my report, but basically that's the idea, is to create a dictionary where each particular cell uh, has its own properties, and based on referring to that dictionary we can see what type of cell it is and what are the equations that need to be solved for that cell. Now the third step is we initialize all the variables, and then finally we march the equations in time. So we iterate each time step. First step is calculating the advection vector, the H vector that I highlighted previously. Because that is already known, we don't have to solve any equations for that. It is a simple algebraic operation for each cell. So first we calculate the H vector. Um, the second step is finding the D matrix. So as I said, the D matrix requires the solving of a linear equation. Fortunately, the D matrix, or it is a diffusion matrix. So with some mathematical changes, it can be reduced into a tridiagonal system of linear equations. One equation in x along the x direction, one system along the y direction. Since there are already libraries available for solving tridiagonal system of equations in the CU sparse library, we can utilize that for this code. So first we do it in the x direction. First we solve the tridiagonal system in the x direction. Then of course, if we have to solve it in the y direction here, so I have used a row based indexing. But if we want to solve it in a y direction, and if you want to utilize the tridiagonal properties, then it needs to be a column based indexing. So we have to rescale the vectors to make it a column based indexing from a row based indexing. So that's the next step. Then once we have changed it to a column based indexing, we solve it using the tridiagonal solve again in the y direction, and we restore the indexing back to a row based indexing. Now since the row based indexing to a column based indexing is a time consuming step, and doing that in each time step can be a big time sink. But fortunately, since each of the particular grid point is independent, and its mapping in a column based indexing is also independent, we can fully parallelize this step, and I have written a kernel specifically for that, so that can be completely parallelized, and that's why we can just broadcast it to all of the threads in the GPU, and each thread can handle one particular grid point and change its indexing order. So that with a GPU, this process becomes pretty fast. In case of a CPU, it would have run into a lot of issues, especially because this step is not properly cached. So once doing this at the end of step 8, which is restoring the right hand side vector, then the biggest step, the most time consuming step, is calculating the pressure, because that is a linear equation. It is not tridiagonal. So we need to use an iterative solver. I have particularly used the biconjugate gradient method, which, as I highlighted, is just a combination of vector multiplications, matrix vector multiplication. So that there was no inbuilt function for that in any of the CUDA library, so I had to write that. But that was pretty simple, because it was just a matrix vector multiplication. So that is the ninth step, which is getting the solving this pressure Poisson equation. And finally, the final step is just updating the velocity with the pressure term, which is the step 2 of our two-step scheme, and then we increment the time step. That's basically the walkthrough of the entire algorithm. So now I'll move on to the results. So this is a validation with a simple test input. The input that we see here is it's an empty box. Initially, it doesn't have any fluid, so the fluid velocity inside is 0. At the inlet, I apply a boundary condition, a parabolic velocity profile at the inlet. So what we would expect is, once the velocity starts coming in, and the top and the bottom sides are symmetry balls, by the way, so it's kind of symmetric about the mid-axis. So what we expect here is that once the fluid starts flowing in, um, the it will kind of fill up this entire container in a parabolic profile. And when I ran this simulation, and the typical results that we see here, I have an animation of the results as well. So we can see as it is playing, we can see that the fluid is entering here and then it kind of propagates through the entire container in a parabolic profile. By about 16 time step, it has already reached a steady state, after which it doesn't change. So this parabolic jet kind of remains in the entire domains. That is the expected behavior which we are seeing with this fluid. So this was with the rho by mu. Rho is the density, mu is the viscosity, rho by mu ratio of 1, which is basically a highly viscous fluid. So it is very thick, and that's why we see that the fluid velocity doesn't propagate as much, and there are large gradients in the fluid. So I have another algorithm here. I'll move on to the next slide. So here is it's another iteration of the same problem, this time with a rho by mu of 1 e power 4. So that is kind of a turbulent flow. It's not a very viscous fluid. It flows smoothly, and since it flows smoothly, we will expect that the flow kind of the gradients inside the fluid are minimal. And if I play the animation, that is kind of what we see here, that in comparison to the older problem where we saw that the velocity profile was well defined and protruding inside, here it is here the velocity becomes uniform only by about 0.2 time distances, and then it's almost green, so it's almost entirely uniform. The other thing is that we see here that there is some choppiness in the solution. That is expected because the flow becomes turbulent, and since in this simulation I have not included a turbulence model, so the numerical stability at higher Reynolds numbers and for more turbulent flow is expected to be low. So this algorithm is going to be unstable for higher Reynolds numbers. Um, So moving on and talking about the same topic, stability with respect to Reynolds number. As I mentioned in the previous slide, that the stability with Reynolds number is a very important parameter in CFD applications. And that is because the equations themselves, the Navier-Stokes equations for fluid dynamics, they have an inbuilt instability in them. The equations are chaotic, which means that there is a particular parameter, and if that parameter increases above a specific value, the equations blow up. And that is what happens in all CFD simulations. The parameter here in this case is Reynolds number that I talked about. So for a large value of Reynolds number, the equations become unstable. And to counter that, a turbulence model is typically used in CFD applications. In my simulation, I have not used a turbulence model, and which is why I would expect that for higher Reynolds number, it will not sustain. The solution will blow up. So I tried to run an analysis of the point at which the simulation completely starts diverging and there is no stability. The results do not make sense. So the time step here is 1 e power minus 5. The time step is fixed. The size of the domain is fixed. What I have varied is the size of the grid sizing. So at the smallest grid size, the maximum Reynolds number after which the flow becomes unstable is 1 e power 5. And then as I increase the grid sizes, the maximum Reynolds number that it can sustain increases. The reason for that being coarser grids employ or coarser grids introduce more numerical error into the solution, and that numerical error usually tends to be of the form of diffusion. So what it does is, if there are any instabilities, it kind of flattens the instability. So that's why a coarser grid are usually able to handle greater Reynolds numbers. But basically the key result that we should take away from this analysis is this: the Reynolds number at smaller grid sizes, 1 e power 5. So this is typical. Usually a flow does become turbulent at a Reynolds number of 1 e power 5. So this shows that this model is able to handle Reynolds numbers up to 1 e power 5. That means it is basically stable for all sorts of laminar flows, and that is a good trait in this model, and that proves that this model is at least able to handle laminar flows, which it is supposed to do. Then another important aspect, since we are doing parallelization, one of the key aspects that we look for when judging the performance of this algorithm is the performance with respect to time, the temporal speed up. And in this actually, so I ran the previous experiment that I showed with a Reynolds number of 1000 and the different grid points. The time step was kept the same. I calculated the amount of time required to execute 200 time steps to reach a stable solution. So this actually gives very good results. So if I plot the execution time with respect to the grid points, it is almost a linear scale up. So that is really good. So that shows that this parallelization has worked and it is giving good results. And why is it giving good results? Because the solution typically contains matrix vector multiplications. If it is run in a serial processor, a matrix vector multiplication is order of n squared. But we are employing a parallel algorithm with a single instruction multiple data paradigm. So all of the matrix vector multiplication steps, all of them happen at the same time, and the matrix vector multiplication is reduced from an O of n squared problem to just a constant time problem. And this proves that the scale up proves that it actually does do that. So it increases in a linear fashion, and that is the best that can be achieved, because ultimately with GPUs there is memory transfer involved, and memory transfer with respect to size is always linear. So the linear scale up is the best that can be achieved, and it shows that that this algorithm does actually achieve a linear speed up. So if this does meet its performance goal, where is the constraint in using this algorithm for generic CFD application? And the main constraint here is the memory. So here, if you can, as you see, I have plotted it only for 40,000 grid points. The reason being, once I started to run with problem sizes more than 40,000, the application started to run out of usable memory. So that is the biggest constraint, that the memory is it just runs out of memory for large problem sizes, and that is a scope for improvement as well, because here I used the CUSparse library given by NVIDIA, and that particularly it requires the allocation of a large buffer size to do its matrix multiplications. That buffer size is what was actually hurting in this case. That is what requires such a large memory. So the scope for improvement in this case is to write an inbuilt code, write a code myself, which does not use the NVIDIA libraries, especially the large buffer size. That is and that can optimize the memory utilization so that this algorithm can tackle much larger problem sizes. Okay, so that was about the performance speed up. Then in terms of the performance of a CFD application, another point that is very important is the numerical stability of the algorithm with respect to the time step. Why is that important? Because till now I have not talked about the time step, which is how much time units we march for each iteration of the simulation. So in the previous slide that I showed the solution in number of time steps. That is the time required to execute 200 time steps. However, the size of that time step is also a critical factor, because say we are running 200 time steps with a size of 1 e power minus 3 seconds and 1 e power minus 5 seconds, the total time of the total simulation time that we actually model varies, and ultimately if we want to model say 10 seconds of simulation time, it impacts, because then we require more number of time steps. Now in general with CFD codes, the main problem is that the time step is the time step for which the numerical solution is stable is dependent on the grid sizes. for smaller grid sizes, that's because if you recall, in all the previous iterations, basically we had a term of delta t by delta x. As delta x decreases, uh, this term multiplied all of the terms, all of the velocity terms. So as delta x decreases, if there are any numerical errors in the simulation, this term increases, and to counter that, this delta t needs to go down. So that is the main problem with CFD simulations, is that if we go for a refined grid size, the delta t also has to go down for a stable simulation. So I ran a few experiments of seeing how much this delta t varies for different del x or delta y sizes, um, which is tabulated here. So as we can see, with reducing delta x, we actually do need to reduce our time step size, which is one shortcoming, because that means that to tackle refined grid sizes we would require more time than expected. But that is the case, as I am not using any preconditioning for the biconjugate gradient algorithm. With a preconditioning, this performance may improve. Uh, in particularly, it may not be completely stable, but at least the scaling of the delta t versus delta x may improve, because what we see here is when our delta x size decreases 4 times, this the dt size increases more than 4 times. It increases 10 times. So that is the scale up is worse than linear. That is one scope for improvement, is to improve this stability, improve the numerical stability of this algorithm by implementing preconditioning. However, the point to note is that since we already achieved a linear speed up with respect to problem size, the lower delta t may not hurt as much as it would do for a serial algorithm, because in terms for a serial algorithm, the execution time itself scales as order of n squared with respect to problem size. Here it's only an order of n scaling, so the delta t may not be that big of a problem as it is for a serial algorithm. So that was a brief summary of the algorithm that I implemented. So the key takeaways from this presentation are, first of all, this 2D CFD solver is fully parallelizable. It demonstrates the power of parallelization, because with that we can actually achieve O of n performance in terms of the algorithm. So that is a big plus for this algorithm. And it is numerically stable for all of the laminar flows. So at least all of the laminar flows would be handled well by this algorithm. It is conditionally stable with respect to the time step, which means that if the grid size is refined, the time step needs to decrease. However, and this may not be a problem, because we already have achieved a good performance with respect to the execution time itself. So that was what this algorithm is. Now there is, of course, a lot of scope for future improvements with this algorithm. First of all is, as I said, as I was running out of usable memory, this code can be optimized for using less memory. Few of the like there are a lot of steps that I've identified where I am using unnecessary memory, and those could be improved. And in particular, the code to do the matrix multiplication, which uses a large buffer size, that could be completely changed to not use as much space as it does. The second thing is, preconditioning can be applied for the biconjugate gradient algorithm that can help improve the temporal stability with respect to the time step. And then so far the algorithm only allows external flows. What that means is just one rectangle. I can apply any boundary condition at any wall that I want, and it will give me the solution. But it is not able to handle any obstacles inside the domain. Like if I put a rectangle here and I want to simulate how the flow goes over these obstacles. So that functionality is not yet available in this algorithm, and that is something that can be added to further improve the functionality of this algorithm. So that was all that I had to present, and thank you for going over this presentation, and please do let me know if there are any questions.